we were talking about probability distributions. So if you did the quizzes from last week, there might be one for this week, I'm not sure. I don't know if I'll one for this week or not. I like this idea. I've been giving it for a couple of weeks now. I like the idea of probability distributions. It's setting up basically a t-chart with values of a random variable, whatever they are. Sometimes they start at 0, up to whatever. And then corresponding probabilities for each one. The main condition is that these things have to add up to what?
1.
Yeah, that's the main condition. You make sure that you've allocated every possible variable value and every possible variable probability. They sum up to 100%, which tells you then that you've accounted for everything. And that's fantastic. If we're doing things like counting chickens, counting the number of times you can play a game until you bankrupt yourself, counting the number of times Sarah Palin gets a guess correct when she's guessing versus not guessing, counting the number of times that Max gets his Crocs on the correct feet, counting whenever you're counting anything, right? But where does that fall short? Where does that fall short? Give me a piece of data that we couldn't count, but that we want to collect. We can't count it, but we still want to collect it. What kind of data would that be? I can imagine snowboarders and skiers right now be thinking about this a little bit. I've been thinking about it, how crazy this weather's been. What's something you don't count, but you're still interested in data-wise? What happened last week? Oh, say that again.
The weather.
Good, what about the weather? To give you one aspect of the weather. I was thinking precipitation, yeah? Snowfall. We'll go with snowfall because it's winter. Well, it's fall, but it feels like winter. It feels like freaking spring today.
Yeah.
Welcome to Bend. So we got how much snow did we get last week? How much snow did you guys get at your houses last week? I got 9 inches on the northeast side of town, which is the lowest point, so it's the warmest section.
Roughly 14 inches.
Roughly 14 inches. There we go. A little bit of variance there. Good, good. How'd you measure it? Did you measure it or did you just kind of eyeball it?
Kind of eyeballed it. Had to shovel it.
I just shovel it. My back says 14. 18. Here we go. Heading getting more uplands. You heading south of town. Oh, in Redmond! Oh, that's right. They had that goofy inversion. It was actually cold.
Yeah.
Yeah, we had more in Redmond than
Got even more than that?
Yeah.
Yes. So all these numbers. So here's the problem. Suppose we try. Don't do this in your notes. But suppose we put those values into this chart, right? So I got 9. We got 14. We got 18. We got more, right? Suppose we got 10. Let's make it even easier. Let's put the 9 and 10 next to each other. Okay. So there's going to be a probability associated with 9. What's the probability that somebody saw 9 inches of snow? I don't know what that probability is, but there is a probability associated with it. Okay, it's not important to know what it is right now at this moment. Just know that there is a probability associated with that. There's also one associated with 10 inches of snow. What's between 9 and 10?
9.5.
9.5?
Yeah, lots of stuff. Yeah.
What else?
9 1/4, 9 1/10.
What else?
You could go forever.
Say that again. Say that again.
You could go forever.
The problem with trying to do it this way with certain kinds of data is you can't. Because you can't infinitely draw number after number after number. It works great for things like counting chickens, but it does terrible for weighing chickens. Are my chickens losing weight? 1, 2? What's between 1 and 2? If you're talking about counting chickens, nothing's between 1 and 2. You can't have half a chicken. But if you're trying to weigh a chicken or weigh an egg, counting the eggs is one thing, weighing the eggs is a different thing. Anything that's measured. So this type of distribution is fantastic when you have discrete data, discrete countable. Remember that old word from back in the day? Oh yes, discrete data. This is a wonderful way of dealing with discrete data. The problem is when you try to deal with, what's the other kind that you measure? You remember this? It's okay if you don't, it's been like 6 weeks. Continuous. When you deal with continuous data, that model falls apart because it becomes too hard to enumerate all of them. Now sometimes we get around it by rounding things off to the nearest ½ inch or nearest ¼ inch or something like that. But that doesn't mean that there aren't things between the ¼ inch increments. So we have a mathematical model for continuity, for continuous data. So as mathematicians evolved, I'll give you some math history here. The earliest mathematics, from what I can tell, was simple counting. simply counting numbers of things like grass seeds or crops planted, like number of corn stalks and things like that. But as math evolved, people began to realize there can be numbers between those integer values. Like there are numbers, as Sandra said, there's a lot of numbers between 1 and 2, or 0 and 1, or 9 and 10.
And you can go to the 0, 0, 0, 0.
Yes, ma'am. Absolutely. So what did mathematicians invent to enable us to discuss this in a symbolic way without having to actually write all of them out? So you might start at 0. 0. So you put a 0 here. What's the next number to the right of 0? Well, as an integer, it's 1. But what's the next number to the right of 0? To answer that question. Because it's infinitely close, but a little bit positive. What is that? See, here's 0 and here's 1, right? Here's 0 and here's 1. How do you represent all the numbers between 0 and 1? What did mathematicians invent?
Calculators.
Even before that, thank you. Calculators. That would have been friggin' awesome. Oh, Titus, we need, here's your TI. What did we invent? You haven't used it probably since Algebra 1, I'm guessing, maybe. Maybe you did, maybe you have. Even if they're bigger than fractions. That's what's so wild. They're even bigger than fractions. Because if you think about fractions like 1/2 and the next fraction next to 1/2, which is infinitely close, there are even numbers between those. Holy crap. How do you indicate them? So you've got 0, and the next number to the right is 0, and the next number to the right is 0, and the next number, and the next number. What's a much easier way of indicating where all those numbers are? Yeah! Just do this! Do that! Remember the number line? Of course you're like, oh God, yes, I remember that back in the day. Draw a line! And say, there they all are. My pencil slid effortlessly from one to the other. That means it covered them all. I mean, it sounds silly, but logically, that's what a number line is. Everything's on there. Now what you do is you trap numbers between. You say, as Sandra said, there are infinitely many numbers between 0 and 1, and here they all are. And here they all are. Now, part of this argument breaks down pretty quickly right now. Going back to the problem we had with this, you had 9, you had 10, and you had infinitely many numbers between. That becomes a problem because then you have infinitely many probabilities, which still have to sum to 1.
Yeah.
So to make our lives a little bit easier, we're never going to ask you with continuous data, what's the chance you are exactly this number? It's like saying, what's the chance I'm exactly 175? What do you think the chance I'm exactly 175 is? I always talk to people about, my weight's 175. I always say it's 175.
Yeah, everybody's either up or down 2 pounds.
Or a fraction of a pound.
Yeah.
So if I go from 173 to 177 over one course of one day, at some point I was 175, right?
Right.
But for what fraction of a second was I 175, right? Mm-hmm. What's the chance I was exactly 175? Go ahead and give it a number. Very, very unlikely, correct?
Yeah.
Give it a number. What's the chance I was exactly 175?
90%.
No, very small number. What's the chance I was exactly 175 on any given day?
Oh, the opposite, 20%.
Yeah, I would say even lower. I'd say it's 0. There's a 0% chance I'm exactly 175 at any given moment. There's a 0% chance. I'm talking right now, right? As I talk, I'm getting rid of moisture in my body and becoming lighter, correct? I'm going to drink out of that thing eventually and put it back in. So maybe for a split second, I pass through that 175, but it's for a fraction of a second every day, right? Now, what's the chance I'm between 174 and 176? What do you think? Pretty good? Not so good. Pretty good? Yeah, that's the kind of problems we're going to be dealing with continuous data. It's ridiculous to say, what's the chance my ponytail is long enough to donate, exactly long enough to donate to Locks of Love, which has to be, I think, 6 inches long minimum to donate. Right? What's the chance it's exactly 6 inches long? 0. There's no chance it's exactly 6 inches long. It's either probably a little bit shorter or a little bit longer. But what's the chance it's at least 6 inches long? 6 or 7 or 8 or 6.5 or 6 1/4 or 7.5 or 7. See the difference? It's easier with a number line to not deal with the infinitely small little tiny ranges on it. It's easier to deal with the large spans of ranges. And that's one of the ones we're going to talk about in this class for continuous data. For these, it's easy to talk about individuals. What's the chance I got 2 girls and 2 boys in my coop? By the way, Agnes has started crowing. like a rooster. I walked out yesterday, 5:30 morning. I'm like, son of a bitch, you just laid a dozen eggs. But it turns out, statistically, every once in a blue moon, one of the girls starts acting like a boy in the coop. I didn't know that. So she can lay eggs and still crow like a rooster. Anyway. But you can say 2 girls, 2 boys. I can't say what's the chance my chicken weighs exactly 1 pound. That doesn't make any sense. Because there's no chance she weighs exactly 1 pound. She's probably around 1 pound, depending on how wet she is, around 1 pound. So that's the kind of questions we're going to be dealing with in this class. So this number line, well, 2, 3, we're going to have negatives too. We'll talk more about why we have negatives momentarily. That number line is going to correspond to the x column over here. Okay? That number line, so I'll make a little continuous versus discrete, little checklist. The number line, number has an E in it. Number line variables correspond to the x's in the discrete t-table. There's more of them. There's infinitely many of them. But they mean the same thing. They are your data. They are your data. They are your data. Okay. So, if they're your data, what's the other column? Where's the P of x column going to be? What do you think? Where's the P of x column going to be? So these numbers that we get, the probabilities that are associated with the x's, where are they going to be on the number line? Any ideas? Any ideas? You have to think, you have to almost think like Math 95, Math 111, Math 60 even in this case. What did you often attach to a number line? A plot, brackets, you're all correct. The most simple construct though is adding a second line, making it two-dimensional. This is two-dimensional, isn't it? Could we plot this before? We plotted these, right? L1, L2, L1, L2. Remember we make histograms of them?
Yeah.
Do the same thing over here. You simply attach a vertical and you create a graph over this number line that shows you where your probabilities are. For example, I'll give you a couple, don't draw these in your notes right now. And the thing about this is, remember that crazy chart I showed you last class of all the different distributions that are out there in the statistical world? Here's an example of one called a Wiley. There's one potential graph that looks like that. This is one is often used when you're talking about the infant mortality and the lifespan of machinery. How many of you guys ever bought something and it breaks almost immediately? You bought something, you take it home and it's broken within a week. That's called infant mortality in machines. It does happen. It doesn't happen often, but it happens more than you would think it would happen. The height of this curve at one end of the number line would imply a high infant mortality. The infant mortality drops off as the thing goes through its normal lifespan. Now there's a very small chance of it failing until it wears out, until it gets too old. When it gets too old, the chance of it failing basically goes off to infinity. Because eventually everything breaks, including the human body, right? Eventually everything wears out and breaks. So that's one way of graphing probabilities. Now that's a great one, but not what I want to talk about in this class. More than we just did. You can also have graphs that look like this. What would you call that? If you were to graph a graph that looks like that, what would you call that? Use one word?
A bell?
Good, a bell or a lopsided bell, maybe a little bit skewed, maybe bell-shaped. If you have it where it's got one tail that's significantly longer than the other, it's usually called some kind of a gamma distribution. This is fun for modeling things that have a propensity for tailing off essentially to infinity, but they've got a low end on one side. For example, if you're measuring chance variation in genetics, that curve is often used, very often used. So that you guys take a bio courses, you might see that curve eventually. If you're taking 244, you'll see that curve with me next term. The one I want to focus on today, though, is not this one. I want to make it even more bell-like for you, Sandra. The one I want to look at looks like this. That's the one. The one from the 10-mark bill. The one from the 10-mark bill. Those are the probabilities associated. So those, the heights of the curve, represent, otherwise this is not pointing in the right place. There we go. The heights of the curve, how high the curve is associated with the probabilities over here. So if you think about it, every single point on this axis has a y value up there, doesn't it? Mm-hmm. And it's a smooth curve. It's not like the histogram that jumped. 1, 2, 3, 4, 5. This is smoothly connected. Smooth it out. Sorry, I didn't mean to. You mean to purge. So the correlation here is that the heights, or the height of the curve corresponds to the p of x's. And technically speaking, they are the p of x's. The height of that curve are, each one of those little y values is a p of x value. Absolutely. The problem is, how do you add up infinitely many p of x's? That's the problem, right? Remember when I did at the store with the guy, I said, there's a 1/3 chance I got a rooster in the box? Well, that was easy to do, because I just added up 1 plus 2 plus 3 plus 4, and I got my answer. The problem is, how do you add up infinitely many things in your mind? We'll deal with that in a second. We'll deal with that in just a second. Yeah, there's a neat mathematical trick. You know how to do it already. You ever taken the area of a rectangle length times width to figure out how big a rectangle is? That's how you do it. We'll deal with it momentarily. So, you see how, well, we'll get back to that point too. Now, that curve right there, the fact that it's symmetric, 0 is supposed to be in the middle. I didn't quite draw it perfectly. 0 is supposed to be directly in the middle. And these guys are supposed to be at fixed unit intervals away from it. When you have a bell curve like that, that's centered on 0, that's the beginning of what's called the quote-unquote standard normal distribution. I'm going to put that right next to it over here. The standard normal distribution. And he's a friend for us, and you'll see why within about 15 minutes. Now, there are lots of bell curves. How many? Infinitely many. Infinitely many. This one's called the standard normal because we like using him to discuss all the other ones in terms of. Much like when you're learning how to read, you learn what the letter E looks like, and the letter T looks like, and the letter Z looks like. And then every sentence you read from then on in, you become more astutely aware of what those letters do. You don't have to relearn the letter each time. You learn it in association with the words it's in. This is the curve that is the learning of the E and the T and the Z and the S and everything else. Is that fair so far? Now, that doesn't mean there aren't other curves. There are lots of other curves. For example, we're going to talk about one today, the IQ curve. The IQ curve doesn't have 0 in the middle, it's got 100 in the middle. The reason for that is the average IQ is 100.
It's 100.
Do you know why? Why is the average IQ 100?
Because they made it the center.
Good! Mathematically, why? You're right. Mathematically, they created this. Linda, go ahead.
Isn't it just that your intelligence quotient is visible by your age, and that's the same?
Right. Intelligence quotient. IQ is intelligence quotient. The way they calculate it is they measure your mental age,
Okay, yeah.
and they divide it by your chronological age. When you divide two numbers that are the same, you come up with 1. So if your mental age and your chronological age are the same, that divided by itself is 1 as a percentage is 100. That's why it's 100. Boom. That's it. So if I'm 41 and I take an IQ test and I test as a 41-year-old mentally, I have an IQ of 100. That's it. Simple. Now, of course, I would never ask you what's the chance my IQ is exactly 100. Because those are two measurements, right? My mental age and my chronological. I'm not really 41. I'm 41 point. I was testing. I was recalculating my mortality for 243 for next term. Remember the quiz you guys did when you calculated my life insurance policy? I wanted to see if my numbers are still the same. So I was calculating my mortality again. And it said for a 41.4-year-old man, I'm like, oh, that's right. I'm not 41 anymore. I was born in June. It should be 41.5, shouldn't it be?
Yeah.
November is halfway through?
Yeah.
Oh no, December is halfway through. So I'm almost 41.5. Anyway, you see what the problem is though? It's not continuous. I'm not 41. And I'm older now than I was when I started saying that sentence. Talking about how old I actually am. You see what I'm getting at? So I'll never ask anybody what your actual IQ is. I'll say, what's a chance your IQ is between, say, 90 and 100? Or 80 and 100? Or 50 and 60? Or 110 and 120? I'll never ask you what the point value on that, because it's silly to do that. It's silly to do that. Now the problem is, you can't answer the question, what's the chance you're between, say, 90 and 100 or 90 and 110, without knowing where the next step is off of 100. See how that 1 is right there, and there's a 2 right there, and there's a 3 right there? That's designed to be that way on the standard normal curve. For the standard normal curve, can you guys see the average is 0? Give me one reason why the average is 0 in that bell curve, in that orange bell curve. Give me one reason why the average is 0.
It's the center.
It's the center. Define which way. I love that, Lloyd. Which way are you defining center right now? Mean or mode?
I
Yes.
would say, yeah, either, any of them.
Any of them, because they're all the same in that curve, aren't they?
Yeah.
Why is the average mean 0 in that curve? Let's go with something easier. Why is the mode 0 in that curve? Why is the mode 0 in that curve?
Highest number.
Highest probability associated with 0. It's the highest point in the curve. It's where the curve turns back down again. Boom, mode. Why is the median 0?
This is the same.
Say that again. It's the same. I heard same and I heard symmetric, both of which I love. Tell me why same. Tell me why symmetric.
The distances are equal.
If you draw a line up from 0 in the curve, what does it do to the curve? Splits it in half. You've got half the area here and half the area here. That makes the median directly in the middle. Thank you. How about the average?
When you add them, take them all together and then re-add them, then that would, yeah.
I like that. And what Sandra's doing is she's nodding to the fact that there are infinitely many numbers on the curve without actually having to add all those infinitely many numbers, right? Because of what you guys just said about the curve being symmetric, she's saying if you add all the negative 2's, they'll be canceled with all the positive 2's, won't they? So when you add those, there's the same number of these. When you add all of these, there's the same number of these. I can't see what number directly to the left of 0 is, but guess what there is?
One on the opposite.
That's going to cancel it. So all the positives are going to cancel, all the negatives it's going to average out to 0. Cookie tray, where would you balance it?
Right there.
Right there. Beautiful. So the standard normal always has an average of 0. Always has an average of 0. Now here's the part that's not inherently obvious. It also has a standard deviation of 1. So when you look at that curve and you see the 1 and the negative 1, this is the range of values that represents one standard deviation. Negative 1 to 1, negative 2 to 2, negative 3 to 3, 1, 2, 3 standard deviations. I don't know why this is why it is, but these things are called z-scores. I don't know why. They just are. They're called z-scores. And I can't tell you why they're called z-scores. The letter z is often used in mathematics. Z in German is the first letter in the word Zahlen, which means to count. So I know when z shows up, if you look at shorthand for number systems, say that again.
You just wrote on the wall.
I did, I'll erase it later, it's okay. If you look at the symbol for integers, it's z, which means countable. I don't know why these are called z-scores, because they're tied to something that isn't countable, so I don't know why that is. Linda, go ahead, you know why? You might know why.
I just wanted to make sure, because I ran into that on the webpage.
You did, z-scores?
Yeah, is that referring to just to the integer? Is that what they?
No, it's really, every single number on that scale is a z-score. I've just highlighted the ones we've talked about in this class a lot, which are the 1, the 2, and the 3's. 1, 2, and 3 standard deviations. We talked about that before with bell curves, right? There's a certain percentage within 1, within 2, within 3. But every number on there is a z-score. 0 itself is a z-score. The 0.5 between is a z-score. The 0.33333, the 0.66666, they're all z-scores. Every single one of them. I've just put a few on. Just like when you were in algebra class, when you drew a number line, you put a few numbers on for reference. You didn't put them all on because you'd still be drawing now from 5 years ago, right?
Right.
Linda, does that make sense?
Yeah.
Every single value is a z-score, my friend. But that's only on this particular axis. Where it gets fun is when we start messing around with the different scales, like IQ scales, human pregnancy scales, speed limit scales, lifespans of headlights. I mean, you can attack almost anything using bell curves. But the problem with having all those bell curves around is you have to have a very, very big book to carry them around in, don't you? Or an app. But the problem, even with an app wouldn't even do it, because how many bell curves are there? Infinitely many. Because you have infinite averages and infinite standard deviations, which means you'd have to have an app that just basically just generates curves all day long. You'd be draining your battery all the time. Constantly plugging it in to recharge. That's annoying. These things die fast enough as it is. So it's better to have one curve that everything refers to. Here's the part of your brain that keeps track of E's and T's and Z's and F's and Q's, and the sound that Q and U make together, and the fact that you can't have a Q without a U, and the fact that the only word in the English language without a vowel is rhythm. I mean, all these things that your brain processes automatically is stored in that curve. Then when you learn a new word and you need a new curve, you just take it back to this curve. So I want to spend today, big chunk of the day, learning about this curve and making sure we can deal with that curve mathematically. Is that fair? Linda, go, please, yes.
Don't forget about mine.
Oh, shit.
Yeah.
Or try.
Yeah.
Or,
I have a first grader too. Sorry.
I was with my family at a math conference about 2 years ago. We were playing Hagman at the table. And this lady at the other side of the restaurant, or across the table from us, saw us playing Hagman with a 6-year-old. And I saw her come over to my son and go, here. And he ran back over. He's like, I got a good one for you, Daddy. And he puts down 6 letters, and I go, there a Y in it? Put 2 Y's in like rhythm. And she's like, how did you know that? And I'm like, well, I said it's the only word in the English language without vowels, which I figured was the reason she gave it to it, but it's had 6 letters. I kind of knew it, but now there's other ones. I must not talk about that now. I feel stupid. But the idea is that curve is like all those little building blocks of language that we have. Every curve past that is every new book, every new magazine, every new sentence you read, every new article you read online. It all refers back to that curve. So today I want to spend a big chunk of time learning about this curve. Is that fair? Mm-hmm. Maybe a little bit. It will be fair the more we go on today. And part of it has to do with the technology I gave you guys last time. I don't want to jump into that right now. So first